Good afternoon, and thank you very much for being here in this session just after the lunch. So we appreciate very much. All of us are still awake, so it's important. Well, my talk is about an efficient implementation of a very well-known string cipher. I have structured the talk in this part. I'm going to briefly present the algorithm SNOW3G, focusing the attention in the linear feedback register in extended field, which is the base of this algorithm. And then I'm going to present the efficient implementation, how we are implemented efficiently these algorithms, and finally some results showing the improvement achieved. Well, the first question is what is SNOW3G? You can see at the slide. Of course, SNOW3G is a string cipher currently used for 3G and 4G mobile communication, third generation and fourth generation. But really, this is not valid for 5G, for 5G generation. Why it's not valid for 5G? Because indeed, SNOW3G has been proposed as a candidate for 5G. It has been evaluated, it has been tested in two parameters, two main aspects regarding the key equivalent size in the data rate. In general, 5G communications need a higher data rate. So finally, SNOW3G is not sure that SNOW3G can achieve this higher data rate. But the main problem is the equivalent key size that is lower than the desirable value. Anyway, SNOW3G is used in the same way in UMTS, and third generation mobile communication, and fourth generation, the long-term evolution. The only difference between them is the identification, the notation used in the two cases, and of course in the initialization vector, because the two systems have several differences in the implementation, but regarding the cryptographic aspect is the same algorithm in two cases. So you can find the specification looking for wherever 3G or 4G communication. The question is why is SNOW3G important, taking into account that it's not valid for 5G. The reason is that most of the observatories in telecommunication, in mobile communication, says that it will be alive for a long time, more or less about 2030. So we need to keep using this algorithm for a long time. So how does it work? This is the general diagram, block diagram of this string cipher. I have enhanced the pseudo-random generator. Sorry. As you can see at slide, this pseudo-random number generator is based on a linear feedback register defined in an extended field, in a field using 32 bits in each cells. Of course, this is not directly. I mean, this linear feedback register does not generate the final key stream. This key stream is combined by a final state machine, but it's not very important in this case because our implementation is only focused in the linear feedback register. So, in general, you can see the main difference between a binary linear feedback register and the same device defined in an extended field. Of course, the output is 1 bit per iteration in the binary case, and n bits per iteration in the extended version. The main problem with the extended version is the complexity of the operations. And finally, the period, of course, is much better in the extended field. The question is that the improvement achieved with the extension field is not n. Is a limit, an upper limit, but it's not possible to achieve because the gain based in the number of bits finally generated, needs a higher complexity. So at the end, the improvement factor is some way much less than n. How can we implement a linear feedback heuristic in an extended field? We have two main methods. A direct implementation, not recommended at all, because the performance of modular operations is too computationally complex. So practical implementation are based in specific polynomials, very specific in such a way that the implementation could be easier. This is the case, the particular case of the string cipher of the SNOW3G. The gx is the feedback polynomial using only two non-binary coefficients, alpha and the inverse of alpha, with the particularity that alpha is a root of another polynomial defined over a different extended field, the Galois field 2 to the 8. And also beta is a root of a different polynomial. This configuration allows us to state these equations in such a way that any element in the Galois field can be expressed by this space. This space has 4 elements, so any element of 32 bits can be expressed using 4 bytes, which is very common in computer science. This implementation leads us to implement the basic operation. The basic operation in this case is only the multiplication of any element in the extended field by the root alpha. So in this case, all of this computation can be summarized in the last equation, where we have only to perform multiplications of several powers of beta. If we translate these equations to code, to codification, we can find that the best way to do that is to use to define a function, a procedure that we have to call several times, many times, 23 times, 245. This is the original, even the official, the standard implementations. You can find it in the official specification of the algorithm, right? So this is our reference, right? Well, our propose is to not to use this proposed official or standard implementation, but to use the binary equivalent model of any linear feedback register defined in an extended field. The figure at this slide shows this equivalent model. In the upper part of the slide, you can see the linear feedback register in the extended field, generating to the right a sequence composed by elements, each element composed of 32 bits, and in the rest of the slide you can see the equivalent model. Equivalent model is composed by n, in this case 32, a binary linear feedback register, all of them with the same feedback polynomial, right? So this is not the result we propose here. What we propose here is the performance, the implementation of this model to the particular case of SNOW3G. So this is the particular case in which the original register of SNOW3G, composed by 16 cells, each cell with 32 bits, a total amount of 512 bits. Now it's turned into 32 binary registers, and each register has a length of 512 bits. The question is that as the feedback polynomial is the same in all of the 32 bits, we can operate simultaneously the 32 bits. We have not to perform different implementation of the 32 linear feedback register. And how can we apply this model from a practice point of view? The question is we need to know which is the feedback, the binary polynomial, the binary feedback polynomial equivalent to the original, to the sequence generated by the SNOW3G. Right? The SNOW3G operated as stated in the specification, I mean in the extended field, generate a sequence, and this sequence has this minimal polynomial, and this minimal polynomial is of degree 512. With this polynomial, of course, has many coefficients compared with the original. The only difference is that this polynomial will be operated in the binary field, and the original is operated in the extended field. So this is the transformation. This is the difference between the two cases: the original to the left and our proposed to the right. So all of these 32 registers are operated at the same time. How? Well, using the same operation, the same instruction of the processor. The XOR operation of the processor takes the same time, the same amount of time. If you can, if you want to operate 1-bit operands than 32-bit operands, because the instruction is the same, and the word length of the processor is 32. So this is the point. So the only thing we have to do is to measure the improvement we have achieved. This is the expression that represents the total time takes by the algorithm. In this expression, we can identify the 3 phases in the algorithm. The first phase is regarding the seed established, and the 2 and 3rd phases are related to initialization phase. It's about 32 iterations without output, and then the iterations of the linear feedback register to generate the final key stream. Right? Well, so applying a very basic notions of improvements in any computer code, we can see that the theoretical improvement is about 2.46, but the practical, the experimental results give us an improvement of 3 times better than the original case. This difference is because we have made several approximations, several assumptions in these computations, so it's much better to obtain better results than the theoretical estimations. So this is the conclusion of a very particular implementation. This work has allowed us to prove that the theoretical model can be applied to a particular and practical case. We have tested that the implementation is really, indeed, is better than the original, and in some way is this implementation is similar to the effect of
that SNOW3G is important and interesting because it will be used in 3G and 4G during many years. And I wanted to know if for 5G and the next standard that are being prepared, are the equivalent algorithms really different, or are they more or the same, just a refined version of this algorithm?
Ericsson has proposed a very similar algorithm. It's based instead of using only one linear Fibonacci register in the Galois field 2 to the 32, they propose to use two linear Fibonacci register in the Galois field 2 to the 16. In these two registers are in some way connected to each other, so the feedback are connected, but it's very similar because the final state machine is basically the same. Even the name is very similar. It's SNOW3G or something similar to that.
Okay.
Right?
Thank you. Any other question? No? So thank you again for the presentation.